All right, this is section 5.1 for stats, probability rules. So blank is the measure of the likelihood of a random phenomenon or chance behavior occurring. That is going to be probability. Probability. All right, it deals with experiments that yield random short-term results or blank, yet reveal long-term predictability. So short-term results or outcomes. We say outcomes here. All right. So it yields outcomes. The long-term proportion in which a certain outcome is observed is the blank of that outcome, and that is the word probability again. So experiments that yield short-term results. Then we have long range or long-term proportion. The long-term proportion is probability. Flipping a coin. If you flipped a coin 10 times, you may not get exactly 5 heads and 5 tails. Okay? But if you flipped a coin 10 million times, it would approach half of one and half of the other. So that's what the law of large numbers says. As the number of repetitions of a probability experiment increase, going from 10 to a million or a billion, the probability with which a certain outcome is observed gets closer to the probability of the outcome. So the probability of a heads when you flip a coin is 1/2, a tails is 1/2. Okay? You roll a die, the probability of getting a 1 is 1/6 if it's a fair die, if it's not loaded. All right? In probability, and blank is any process with uncertain results that can be repeated. It's an experiment. An experiment. Experiment is any process with uncertain results that can be repeated. For example, if everybody in stats took a coin and flipped it 10 times, we would be conducting that many different experiments. Okay? Provided we had a fair coin and we flipped it the right way or whatever. And we possibly could have somebody even in our class get all 10 heads or all 10 tails. But if we add all those together and say we flipped it, 300 times if there's 30 people, then now we get closer probably to 150 and 150. It may not be exactly. In fact, if it was exactly, I'd say we didn't do it. We probably just made it up. Okay? So, but the sample space, S. So sample space is denoted by a capital S. The sample space S of a probability experiment is the collection of all possible outcomes. An event is any collection of outcomes from a probability experiment. An event consists of one outcome or more than one outcome. We will denote events with one outcome, sometimes called simple events, E sub little I. In general, events are denoted by using capital letters such as E. So in other words, an outcome is the result of one trial of a probability experiment. The sample space is the list of all possible results of a probability experiment. So if you flipped a coin, say 3 times, you could either get heads, heads, and heads, or you could get heads, heads, and tails, or you could get heads, tails, and heads, tails, heads, and heads, right? We could go through this in a bunch of different ways, right? You could get heads and tails and tails. Each one of these are different outcomes of flipping a coin 3 times, right? So there's just an example of an outcome, right? An event, I should say, an event, all right? So rules of probabilities, the probability of any event, P, the probability of P, I said P. The probability P of E must be greater than or equal to 0 and less than or equal to 1. 0 means it never happens. 1 means it always happens. Probability is somewhere between the two, but it can be one or the other. It can be equal to, if you notice. And the sum of all the probabilities must be equal to 1. That is the sample space S of all these events. If you add all those probabilities up, it's got to be 1. It's got to be 1. So a blank blank lists all the possible outcomes of a probability experiment and each outcome's probability. Excuse me. It's called a probability model. All right? Probability model. A probability model must satisfy the rules 1 and 2 that we just saw, right? Every probability is between 0 and 1, and the sum of the probabilities is 1. Exactly 1. Not close to 1, exactly 1. All right? So here, the color of plain M&Ms. All right? The color of plain M&Ms can be brown, yellow, red, blue, orange, or green. Suppose one is randomly selected from the bag. Table 1 shows the color and the probability of drawing that color. And M&M's is the source here. So to get a brown M&M, you got a 13% chance, a 14% chance yellow, 13 for red, 24 for blue, 20 for orange, and 16 for green. So I'm saying percentages, but it's a proportion, right? 0.14, 0.13, 0.24, whatever, okay? So is this a probability model? Well, first of all, are all of these numbers between 0 and 1? Yep, they are. And then if we add them all up, so 1, 2, 3, 4, 5, 6, 7, 8, that's 8 tenths. And then 2 3s and a 4 gives me another tenth, and 4 and 6 gives me another tenth. That's exactly 1. And that's what they did here. They added it up and it was exactly 1. They're all between 0 and 1, and they add up to 1. So therefore, this is a probability model, okay? This is a probability model. It works out. If an event is impossible, the probability of the event is, well, I told you if it never happens, it's 0. If an event is a certainty, the probability of the event is 1. Okay? For instance, if there is a pack of M&Ms on the desk, it is a 100% chance that I will eat them because I like M&Ms. No, I'm just kidding. I'm not going to steal your M&Ms. Okay? But the probability of the event is 1. The probability of the event is 0 if it's impossible. If it's a certainty, it's 1. An unusual event is an event that has a low probability of occurring. Okay? Now, I'm going to tell you this, but it's not always the case. Typically, the cutoff is 5%. Okay? It's typically, I should put typically. Typically, the cutoff is 5%. Okay? But it's not set in stone. So I'm going to write that too. Just so you don't say, well, you wrote it down and didn't tell us that. But not set in stone. Okay? So if you did something and said, oh, it's only a 7% chance, I think that's that's unlikely or unusual. Well, okay. I might buy it for 7%. But if you said 2%, then most everybody's going to say 2% because 5% is sort of that universal cutoff, but not set in stone. Right? Again, if you got something that was 5.3% and you did an experiment and you didn't know what the true proportion would be, if you did it, a million times with the law of large numbers, you might say, you know what, this is close enough, I'm going to call this unusual. All right? Approximating probabilities using the empirical approach. The probability of an event E is approximately the number of times event E is observed divided by the number of repetitions of the experiment. So, empirical approach, you are doing experiments, flipping the coin 10 times, like we said, not thinking about the number of outcomes and how many ones are possible and all this other stuff. We're actually doing experiments. When we find probabilities using the empirical method, using evidence based on outcomes of an experiment, the result is approximate because different trials lead to different outcomes and therefore different estimates of our probability of E. Again, if we all flipped a coin 10 times, we wouldn't all get 5 heads and 5 tails. Yours might get you 70% of heads and 30% tails, and somebody else may be 80% tails and 20% heads. Again, but if we start to look at that over and over and over again, it'll kind of centralize there based on the law of large numbers if we do it enough. All right? Flip enough coins. The classical method of computing probabilities does not require an experiment. Rather, it relies on counting techniques. The classical method of computing probabilities requires equally likely outcomes. If it has equally likely outcomes, it has the same probability. So this is that fair die that I was talking about. If you throw a fair die once, you're going to get one of 6 things. 1, 2, 3, 4, 5, 6. If the die is fair, what I mean is not weighted. Some die are weighted, believe it or not. Okay? And so, if I had a game and I wanted you to roll a 3 to win, I might weight it so that 3 comes up less often than the other 5 numbers, right? That'd be cheating, but they're out there, okay? Just want you to know that. So, but if it's a fair die, then you have a 1/6 chance of getting a 1, a 1/6 of a 2, a 1/6 of a 3, a 1/6 of a 4, and so on and so forth, all right? And then contrast this with the loaded die, which 5 and 6 is twice as likely as 1, 2, 3, and 4. That's not, you can't do the classical approach with that. All right, computing probability using the classical method, it boils down to this: the number of ways an event can occur over the number of possible outcomes. Okay? So if we wanted to say, the probability of getting the sum of 7 when you roll 2 die. Well, if you sum to get 7, you get a 1 and a 6, you get a 2 and a 5, you get a 3 and a 4, you get a 4 and a 3, you get a 5 and a 2, and you get a 6 and a 1, right? If you count the one dice versus the other dice, okay? One die versus the other one. So this happens 1, 2, 3, 4, 5, 6. 6 ways. Happens 6 ways. And if you think about 2 die, you have 6 possibilities on one and 6 in the other. You have 6 times 6 ways those can be tossed and land. So you have a 6 out of 36 chance of getting a sum of 7. So that's what this is saying. This is not an experiment. This is me using equally likely outcomes to say that. All right? So, and we're going to learn more about that whole 36 thing that I just said later on. All right? So here, if a sports reporter is asked to ask what he thinks the chances the Red Sox play in the World Series, the reporter would likely process the information that they know about the Red Sox, i.e. their pitching staff, their leadoff hitter, their so on and so forth, right? Injuries, that kind of stuff, and then make an educated guess. The reporter may respond, there's a 20% chance the Red Sox will play in the World Series. This forecast is a probability and is not based on, relative frequencies. And look, can we repeat the season a bunch of times, like 1,000,000 times, and see if the Red Sox get there 20% of the time? No, you can't even play the season again, okay? So, look, and you can't play it under the same circumstances, same players, same schedules, even the same age, right? If we played it again, they'd be older or younger or whatever. So the forecast of 20% does satisfy the criteria of a probability between 0 and 1. This is known as subjective probability. And a subjective probability of obtained on the basis of personal judgment, and it is legit. I mean, it is if it comes from a sports reporter. If you just ask me what's the probability that the Red Sox play in the World Series, I don't study the Red Sox. I don't study baseball that much. I love baseball, watch it when it's played, but, subjective probability, it's okay here. Another perfectly legitimate example here is a financial reporter may ask an economist about the likelihood the economy will fall into a recession in the next year. Well, we can't conduct an experiment n times, right, and then figure out how many times we go into a recession. We can't do that. So the economist uses his or her knowledge of economy and things that are going on to the current conditions and says, here's my educated guess of what's going to happen. All right? And then there are still things the economist doesn't know, or the sports reporter. I mentioned injuries. What if the Red Sox 3 best pitchers all go on the DL, season-ending injuries 1 week before the playoffs? They're probably not going to the World Series, even though they may be in first place by 15 games at that point. Right? There's just things we can't control. All right? So this is lesson 5.1 for stats.